Or we can see things that experimentalists cannot see. If you look at a material at the atomic scale, this is very difficult to characterize. It's very hard to see atoms in a microscope. While if you do modeling, you see atoms by default, so you can see structural properties, you can see defects, you can see interesting things happening in the material in the conditions you want to and with the resolution you want to. If you are working, for example, in fusion or fission, right? If you have to work with radioactive materials, it's better if you can do it in a computer, and it's safer for us, and you can actually do things that cannot be done in an experiment, or because there are no infrastructures for that, or because they are too expensive or too dangerous. I am Julio Gutiérrez. I am the leader of the material science group at BSC. I started working in the center in 2020 when I joined the fusion group led by Mervi Mantsinen, and after 2 years working at the fusion group, I got promoted to a new position leading this independent group in material science. We work on materials modeling at the atomic scale. So we use atoms as fundamental building blocks of materials. We know that these atoms in a material, they stick together due to the interaction between electrons. So we solve models in the computer that tell us how electrons interact with each other. Based on those interactions, we can understand fundamental properties of materials, looking at them from the electronic and atomic point of view, and we can model materials for new applications. We work mostly on materials for energy. So one example are materials for photocatalysis. These are materials that can split water, so we can convert water into hydrogen only with the energy of a sunlight. We also work on other applications related to energy. We work on batteries. We work on environmental applications such as water filtering, sensing, biomaterials for orthopedic implants. So there are a lot of things you can model starting from atoms and that have real applications in technology and engineering. So the two main projects we are working now are, one is the MAX Center of Excellence. In that project we work on several ab initio computational material science codes, and we try to adapt them to run efficiently in supercomputers of the scale of Moreno 5. The other project I work on is called MLAL. In that project I am the coordinator, and we work on the design of photocatalytic materials, which are, as I said before, materials that can convert water into hydrogen only by taking energy from the sun. And this is a collaboration with institutes in Japan and Turkey.